shall we? Oh shit, there's a new update. I haven't streamed in so long. This is gonna be scuffed. Authorize. Yes. Okay. Seems to be working. Okay, how do I used to set this up? I think like this, and this, like this over. Oh my god. Hey Chow. What's up? I'm alive. Are you alive? Also, you're not gonna enjoy this stream, I suspect. I have gone back to uni. I am a student of the sciences, and I'm not gonna be doing politics here. I'm gonna be doing some studying, is what I'm gonna be doing. Though if you want to hang out and listen to me ramble about mathematics, then that's gonna be cool. How are you doing, by the way? We haven't talked in like forever. Yeah, fuck politics. Fuck politics. True. Oh, dude. Okay. I did say I wasn't gonna talk about politics, dude. The far right parties here in France basically won the European elections in France. So Macron decided to dissolve the parliament. He's dissolving the parliament so now the far right parties can win the win the parliament. Awesome. I love that. I love it so much. We're gonna get there's some shit going down here in France if you're interested as a political science student. Holy fuck, it's you. Yes, it's me. How are you doing, Derek? All right. But yeah, we're not gonna talk about so yo-yo. We're not gonna talk about French politics. We're gonna talk about complex analysis. So this is one of the books my my professors this year recommended. I studied during the vacation. This is the Conway's Functions of One Complex Variable. So basically this year we did pretty in-depth intro course to analysis. I'm fluctuating between highs and lows, and I'm currently at a low. Oh no, that sucks. And hey, I guess the positive way to look at it is there is no way else than up from there. But seeing you though made my day better. Aw, I'm glad it did. I was gonna ask you if there's anything I can do, or if you want to chat off stream or whatever. I'm there. I don't seem to be there, but I was there. I am there. Don't hesitate to hit me up if you need to chat or like bitch about something. So the way this book was presented to me, my professor told me that it's basically complex analysis is, according to her, one of the most beautiful parts of mathematics. So it's like very elegant, very beautiful, and I'm looking forward to it. I'm a bit of a pedant when it comes to reading this kind of stuff. I'm reading the intro. I know people usually skip the intros. I'm reading everything, so thanks will do if I need. Yeah, really don't hesitate. Lower the music volume. This book is intended as a textbook for a first course in the theory of functions of one complex variable for students who are mathematically mature enough to understand and execute epsilon minus delta arguments. Or no, epsilon delta arguments. Yeah, so epsilon delta arguments means the. Oh yeah, let me hook up my tablet. Actually, I'm gonna need it. Let's finish setting up for the stream, so I can have a whiteboard on screen. So for anyone unfamiliar with analysis, that means that's like going back to the definitions of like what's a limit, what's yeah, it's mostly for limits, but from limits you get derivatives and all that stuff. Let me open up a Canvas webpage, canvas.io. I know it's canva.io. I was confused. No, okay, never mind. Oh, canva.com. God damn it. Whiteboard. All right. There we go, and there we go. Okay, perfect. We got a whiteboard. Where was I at? So the definition of a limit, for example, for real numbers, right? It's for all epsilon strictly positive. There exists a delta strictly positive such that for all x belonging to a function f's domain, the distance between x and a being the point where we're studying the limit, being inferior to delta, implies that the distance between f of x minus L being the limit, is lesser than epsilon. Then you got all the variants. Oh wait, let me fix this is, there we go. Now it's the right size, and I guess I need to zoom out. Okay, perfect. So this is the definition for a limit in a specific point, a finite limit as well. Then you got variance depending on whether you're going infinite or not. A more general but less like useful version, I guess, would be the how do you say it in English? Okay, so this is going to be a big part of the stream. It's going to be me figuring out what are the like English technical terms for mathematical terms I learned in French. Voisinage in English, mathematics, and neighborhood. Okay, mathematics. Neighborhood. Okay, cool. So if we take so for all, okay, so if saying that the limit in A of f equals L, that is, oops. That is the definition using neighborhoods would be that for all wait, let's call it U. For all U being a neighborhood, let's call neighborhoods with V, because in French it's voisinage, it starts with a V, that's what I'm used to. For all neighborhoods of L, there exists a neighborhood V of A such that x belonging to the neighborhood of AV implies that f of x belongs to the neighborhood of LU. I'm in the neighborhood of your V. Nice, good one. Hey, you got me. This is a more general definition, because then you can use because then L, for example, if we're in dealing with real numbers, L can belong to R union plus minus infinity, and that's really convenient, right? You don't have to have like 4 different versions of the of this like specific yo, thanks Fate for the sub, of this specific proposition. You don't have to have like four different versions of it. You can just, but the problem is it's not, you can't actually do proofs. It's much harder to do proofs with the neighborhoods. With this version you can do like direct proofs. Anyways, enough for the tangent. We are going back to this. So that's where the epsilon delta arguments comes from, right? It's from here. This it's talking about this specific epsilon, this specific delta of the. How do you see you back and doing something you enjoy? Thank you. Gotta run some errands. Be back later. All right, see you. Topics from advanced calculus that are used. Leibniz's rule for differentiating under the integral sign are proved in detail. I like that. The actual prerequisites for reading this book are quite minimal, not much more than a stiff course in basic calculus and a few facts about partial derivatives, so that's good. I don't know much about partial derivatives. I might have to, I might end up having to do some research into them. Which is one of the things I was planning on learning, because next year for physics class I'm going to be needing to master partial derivatives. Complex variables is a subject which has something for all mathematicians. Nice. It's inclusive. In addition to having applications to other parts of analysis, it can rightly claim to be an ancestor of many areas of mathematics. Homotopy theory. Oh, it's LGBTQ friendly. Manifolds. The view of... I have no idea what those things are. I mean, I've seen them. I've seen those words thrown around. Manifolds, or... Well, maybe not homotopy, but topology, I'm assuming, is the relation, perhaps. This view of complex analysis as an introduction to mathematics has influenced the writing and selection of subject matter for this book. The other guiding principle followed is that all definitions, theorems, etc. should be clearly and precisely stated. Proofs are given with the subject in mind. Most are presented in detail, and when this is not the case, the reader is told precisely what is missing and asked to fill in the gap as an exercise. Nice. I like exercises. The exercises are varied in their degree of difficulty. Some are meant to fix the ideas of the section in the reader's mind, and some extend the theory or give applications to other parts of mathematics. Occasionally, terminology is used in an exercise which is not defined, e.g. group, integral domain. Oh yeah, that's another thing. Mental note for myself. We've used structures this year because we've seen vector spaces, and the definition of a vector space is basically a structure, but we haven't really learned what are groups, what are like other structures than vector spaces. So that is something I'm going to have to study on by myself as well. Chapters 1 through 5, sections 6.1, 6.2 are basic. It is possible to cover this material in a single semester only if a number of proofs are omitted, except for material at the beginning of blah blah blah. The book is independent. Chapter 7 initiates the student in the consideration of functions as points in a metric space. Okay, metric space I think is a space where you have a norm. Is it called that way in English as well? Like what I like this here. This function, that's in French we call it the norm. And like that's what allows you to measure distance between points, right? You can do it in you can define it in for complex numbers, for any like r to the power of n spaces, that kind of stuff. So like spaces where there's no ordering, right, in complex numbers or in multidimensional vector spaces like Rn. But there is distance between points. I think that's what it's referring to. Actually, let's check. Let's just check the Wikipedia article real quick. Metric space definition. Metric space is a set together with the notion of distance between its elements. Yeah, exactly. Okay, that's it. That's it. I got it. Oh my god, I'm so good. I'm so good. I understand words. The results of the first 3 sections of this chapter are used repeatedly in the remainder of the book. Sections 4 and 5 need no defense. Moreover, are you defending? Moreover, the Weierstrass factorization theorem is necessary for chapter 11. Yeah, I'm gonna skip this part of the intro. I don't really know what they're talking about. Spoilers. The remaining chapters are independent topics and may be covered in any order desired. I'll just go in the order of the book. Yeah, okay, like this part of the intro is clearly for professors, like using this book to prepare their class, so like I don't really need to read that part. Picard's theorem, oh shit. There are other topics that could have been covered. Some consideration was given to including chapters on some or all of the following: conformal mapping, functions on the disk, elliptic functions, applications of Hilbert space methods to complex functions. But the line had to be drawn somewhere, and these topics are the victims. For those readers who would like to explore this material, the topics covered in this book, the bibliography contains a number of appropriate entries. Most of the notation used is standard. The word IFF is used in place of the phrase if and only if, of course. The symbol, the square symbol for the end of a proof. When a function other than the path is being discussed, Latin letters are used for the domain, and Greek letters are used for the range. Okay. This book evolved from classes taught at Indiana University. Okay, cool. Preface for the second edition. I don't think we care. That's the contents. What the fuck? Hey, Jokesta. How are you doing? It's been a while, hasn't it? I warn you. This is a big brain stream, okay? No more drama, no more. I'm not gonna be. Well, I may from time to time if I stream regularly or whatever. You know how it goes, chatting about stuff. I'm back in university. I just finished my first year. Decided to get a diploma and pursue my dream of becoming a scientist. And went through it really well. And since now I'm on vacation, I've decided to continue studying while I'm on vacation, because there's a couple different books some professors recommend to me and other stuff I wanna look into. And I figured it would be fun to stream it. So there you go. What subject? I'm doing a double degree in mathematics and physics. That way I can wait until I get my double bachelor's to choose whether I want to continue in mathematics or physics. I'll probably continue in physics, but having the stronger mathematical background is really, really valuable for what I want to do, because I'm really interested in theory and quantum mechanics and stuff like that, where having the stronger mathematical background is going to be really, really valuable. And honestly, just because I really like mathematics and physics, so. We denote the set of all real numbers by R. Super cool, you're an inspiration, bro. Oh, thank you. I appreciate that. And to be fair, also, it's a lot easier in France. My tuition was 300 euros for the entire year, compared to American education costs. So I understand that depending on where you live and what kind of school you want to go to, obviously your mileage may vary on whether it's feasible to go back to school or not. But that being said, obviously you can go back to school at any age. And I have so many examples too in my life that really helped me make this decision. I have a friend who's just now, he's the same age as me, he's just now finished his master's, and he's going for a PhD in philosophy. An old friend's dad, he'd gone to med school in his late 20s, early 30s, which basically means you're starting your doctor's career at 40. And he ended up being head of the anesthesiology department in a big hospital. He had a great career. Yeah, it's never too late to learn, right? I believe when you stop learning is when you stop living in a weird way. Which doesn't mean you have to go back to school to learn. Obviously, you can learn in day-to-day life. Anyways, enough rambling. We denote the set of all real numbers by R. It is assumed that each reader is acquainted with the real number system and all its properties. I assume people listening here are as real numbers. You probably know them. If anyone has questions, don't hesitate to ask me. In particular, we assume a knowledge of the ordering of R, the definitions and properties of the supremum and infimum, sup and inf, yes, and the completeness of R. Every set in R which is bounded above has a supremum. Okay, this is actually really cool, because this is, like, the supremum and infimum is stuff we've really studied in depth this year, and manipulated in different ways. It's really cool to see it being applied in like further subjects. I knew it was like important, but because I had a discussion with fellow students where the professor we had this year was like very like kind of the stereotype of the hard ass maths professor, like super strict, super pedantic, very how do you say it in English? Has a very high expects our proofs to be written at a very high standard and stuff like that. The result is, out of 300 people who took the final exam, only 20 of us have above 50%. Literally, only 20 people out of 300 got above 50% in his class. I got a 16 out of 20, and that was the best grade this year. Yeah, I took an organic chem class like that. Yeah, and it's like, I understand it's super frustrating if you're not really into the subject, but when you are, that kind of professor is so good. Like, they're pushing you, to be better. And not in the, like, toxic whiplash Fletcher way of, like, pushing you until you either break or make it. But just like pushing you to better yourself, to satisfy a higher standard and all that stuff. And like reading this, I'm really grateful for it, because he could have skipped a lot of stuff. He could have skipped like a lot of, or like gone easy on us on a lot of this stuff. And like reading this new book I want to study, I'm like, wow, no, I'm ready for this now. Thanks to him. It is also assumed that every reader is familiar with sequential convergence in R and with infinite series. Okay, so I haven't yet had a class on series, though we saw a little of them this year, but I am familiar with sequential convergence. If the translation is correct with French, sequential convergence is being able to it should be the fact that you can find get the limit of a function by plugging in a sequence into the function. We've only used it to prove when functions diverge, when they don't actually have a limit. That's what we used it for this year. Let me just make sure it's what I think it is. Sequential convergence mathematics. On sequential convergence. Okay, I think what they're talking about is just limits of sequences, which yeah, I've studied that this year, so we're good on that prerequisite. Finally, no one should undertake a study of complex variables unless he has a thorough grounding in functions of one real variable. Although it has been traditional to study functions of several real variables before studying analytic function theory, this is not an essential prerequisite for this book. There will not be any occasion when the deep results of this area are needed. Cool. The field of complex numbers. We define C, the complex numbers, to be the set of all ordered pairs, A, B, where A and B are real numbers, and where addition and multiplication are defined by the following properties. Interesting. So this is a construction of C that doesn't even use the square root, big quotes, of -1, the I number. It is easily checked that with these definitions, C satisfies all the axioms for a field. Okay, a field, is that the vector space meme? Is that the English term for a vector space? A field is a set on which addition, subtraction, multiplication, and division are defined and behave. Oh no, it's much more than a vector space. Okay, a field is like the biggest, the thing where everything is defined, basically. You got your inverse of addition, inverse of multiplication. Cool. Okay, just making sure I'm brushing up on my English lingo since I'm taking my classes in French. That is, C satisfies the associative, commutative, and distributive laws for addition and multiplication. 0, 0, and 1, 0 are identities for addition and multiplication respectively, indeed. And there are additive and multiplicative inverses for each non-zero element in C. Oh shit, is this the... Yeah, it's the Deus Ex music. Nice. I got a playlist running in the background. I don't know if you can hear it. We will write A for the complex number A0. This mapping, A to A0, defines a field isomorphism of R into C, so we may consider R as a subset of C. I agree. If we put I equals 0, 1, then AB equals A plus BI. Yeah, this is where we're building complex numbers. From this point on, we abandon the ordered pair notation for complex numbers. Yes. Note that I squared equals -1, so that the equation Z squared plus 1 equals 0 has a root in C. Indeed it does. In fact, for... Wait, doesn't... Isn't it a double root by the what BT dubs? Or am I... Yeah, it's a double root, right? And that's just really pedantic, but Z squared plus 1 equals 0. It's going to be equivalent to Z plus I factor of Z minus I equals 0. Wait, so it's not a... Wait, so no, it's I and it's plus minus I is the two roots. Okay. Anyways. In fact, for each Z in C, Z squared plus... Oh yeah, that's literally the next sentence in the book. Is Z squared plus 1 equals Z plus I, Z minus I. I like doing this though. When I'm studying, I really like whenever I have an idea, rather than continuing to read, I'll try to like work on, even if it's like a very simple idea, like just here. I'll stop reading the book and I'll do it myself, and then go back to the book, or whenever there's a proof, like I'll try to do the proof myself. I'm not going to necessarily succeed, but getting the practice in, I think, is important. More generally, if Z and W are complex numbers, we plane Z squared plus W squared equals Z plus IW multiplied by Z minus IW. Interesting. I've never seen this identity, actually. We've never had to use it, I guess, but that's a cool one. I think the way it works is we got Z squared plus W squared equals Z squared plus... No, right. Z squared minus IW squared. And then we can use the identity of A squared minus B squared equals Z plus I... ooh, that was an ugly W. IW Z minus IW. Nice. And obviously you can just develop the right-hand side and see that it matches. By letting Z and W be real numbers A and B, we can obtain, with both A and B different from 0, 1 over a plus ib equals a minus ib over a squared plus b squared. Oh yeah, this is just the formula for the reciprocal of a complex number. Name on stream, what year is this? I know, right? It's a boring stream. It's it's not really homework because no one's assigned this to me. No one's expecting anything from me. I'm just working on I'm just doing some whatchamacallit, studying some mathematics book. You can hang out if it interests you. When we write C plus, so yeah, this is just basic complex number properties. Where Z equals a plus ib, we call a and b the real and imaginary parts of Z. This is just like really basic stuff about complex numbers, but doesn't hurt to reread it. We conclude this section by introducing two operations on C, which are not field operations. If Z equals x plus I y, then we define the absolute value of Z. Yeah. This sure is the absolute value. Well, that's the distance. It's a metric space. We were talking about that earlier. And the conjugate, yeah. In particular, if Z is different from 0, then 1 over Z equals a conjugate of Z over the absolute value squared. Yes, that is the same as what's written here, by the way. The following are basic properties of absolute values and conjugates whose verifications are left to the reader. I'm not going to verify them. I did that this year already. This is really basic stuff. Yeah, the real part of Z is half of Z plus the conjugate of Z, and the imaginary part. Also, once again, if anyone has questions, I love explaining stuff. I'll go more into detail about parts I'm going faster on. The reader should try to avoid expanding Z and W into their real and imaginary parts when he tries to prove the last three. Rather, use 2.1, 2.2, and 2.3. Okay, wait, I like a challenge. Wait, how do I prove those without expanding them into their real and imaginary parts? Let me think about this for a second. Wait, they're saying use 2.2, but 2.2 is expanding them into their real and imaginary parts. Interesting. Huh. I mean, 2.5. Okay, let's just do 2.5 for now. 2.5 is going to be easy, right? What are we proving? We are proving that the following thing, that Z over W with ZW belonging to C squared equals modulo of Z over modulo of W. I'm calling the modules because of French education, but it's absolute values, right? I think the easy way of doing it is, let's do like a dot here for where we start our proof. It's like without expanding into real and imaginary parts, the easiest way would be to start from here. This is equals, we're going to use the property, the previous property back there, which was that 1 over W. Wait, so we basically got Z multiplies 1 over W, which equals z multiplies the conjugate of w over the square of the absolute value. I don't know if that actually helps. I don't know if that actually helps. Because we're not using a lot here, are we? And we got this. Oh, wait, I might have an idea. So we got 2.1, 2.2. Like, this shit's really easy to prove, but not if you're limiting yourself to very, very few properties. And the book says we shouldn't expand them into real and imaginary parts. Okay, let's just do them in order. Let's start with 2.4. Because if we have 2.4, then we can easily prove 2.5. I think I'm wrong to do them in this weird order. And to do 2.4, okay, I have an idea. Tell me in words why you think it would hold. Wait, what do you mean? Let's just prove the other one. That one, I think that I have a good idea. So we're trying to prove that z multiplied by w equals zw, but without expanding real and imaginary parts. We are going to do that by having z multiplied by w equals I can multiply above and below. If I assume, oh wait, I can't. Can I assume anything about them? Because I kind of need to. Okay, we're gonna just separate them. We're gonna postulate something. If z different of 0 and w different of 0, because then I can multiply and divide by the conjugate. Is this actually a good idea? Alpha just okay, this might not be a good approach. I don't see how you're supposed to do it without expanding into real and imaginary parts. So, because then we use this property, right? We get the we get z squared up here multiplied by the absolute value of w squared. And we get this. So those are just real and positive numbers. I think we're allowed to use that property, right? The absolute value of z and the absolute value of w are both squared. They're just real positive numbers. We can take them out of here. Then I'm multiplying this by this. Okay, is there any other property we can use here? I think we're gonna use this one, right? Or like this one? I'm not sure. Man, this is so much easier when you expand. When you expand the real and imaginary parts. Because obviously this is worth... The absolute value of this is 1 over the absolute values of C and W, and then you're going to end up with this and this. But I don't know how to, like, justify the detail here. Let's just continue. Like, I'm not sure how much I have to justify or detail. Anyways, we can use that other property back there, which allows me to say I'm just looking at the conjugate of the product of Z and W in here, and then the inverse but that's just gonna take me back around this. I think? Well, I think that's okay, actually. I think that's okay. So then 1 over this complex number is also equals to the conjugate of this, but this is already the conjugate, so the conjugate of conjugate is the same. So I get Z multiplied by W over... But this is just running around in circles. Not actually proving anything here. Oh, also. Yeah, okay. I don't actually understand what the book wants me to do. we did this. We did this in class, but we used the expanding into real and imaginary parts when necessary, so I'm really not sure. What class is this, by the way? Complex analysis, yes. I already had a complex numbers class, so like those properties and stuff we already did prove. I was just interested because the book suggests I should try to avoid expanding Z and W into the real and imaginary parts when proving those last 3 properties, and I don't find that easy, like, at all, with that extra condition on it. Okay, I think I'll just skip this for now. It's not... It's nothing really that interesting. There's just like a trick I'm missing. Or it's something... Or it's like some extra properties that haven't been described here that are assumed we can use. Find the real and imaginary parts of each of the following. I'm gonna skip this for now, actually. I do not... Well, this could be fun. I to the power of n as, well, 1 over square root of 2 plus I over square root of 2 to the power of n. And that one's fun because you can use the exponential form of the complex number, right? So 1 plus I over square root of 2 to the power of n with, what was n belonging to 8. That's, this here is equals to, oh my god, please stop, just go to the physics book instead. What is this nerd shit? Hey, you were warned, this is going to be nerd shit. This is e to the I pi over 4 to the power of n equals, I suspect the book doesn't want me to use the exponential form of complex numbers, but this kind of shit is so much is so much easier when you're using the exponential form. Actually, we're even gonna, let's do it like this. And then that means the real, so yet the real part of this is going to be cosine n pi over 4, and the imaginary part is going to be sinus n pi over 4. But OneNote is free, I think, and you can sync and shit, but it doesn't work on Linux, I think. I'm not using Linux anyways. Yeah, sorry, Derek. If you want to, I mean, I really like mathematics, so I'm going to be doing mathematics. I'll figure out a schedule. I'm not going to be just doing this book and then just doing another book. So I'll do some physics shit too. But today it's complex analysis. All my notes were on OneNote if they were handwritten. Nice. Find the absolute value and conjugate of each of the following. No thanks. Show that z is a real number if and only if z equals the conjugate of z. Oh, that's an easy one. So what we're trying to show that z belongs to R if and only if z equals conjugate of z. So the way I learned to prove those kinds of things, we're going to do them in one direction and then in the other, which sometimes you can do that in a simpler way, but I like doing it this way. Regardless, unless I see an obvious way where we don't need to do the both directions. So this direction, we're assuming let z be a real number. Well, the definition of conjugate means that it's very confusing to write it as in this way, though. I'm just gonna fix the notation here. Z is a complex number such that the imaginary part of z equals 0. So z is a complex number. Imaginary z equals 0. Oh my god, it's the same person from last time. Are you married now? No, we are not. Quelqu'un qui disait que c'était qui a remarqué que tu étais la même personne qu'il voyait à l'époque derrière moi dans les streams, et qui lui demandait si on était mariés. Pourquoi pas. Bah, on voulait pas.
No.
She just kissed the headphones, by the way, not me.
I'm married to the headphones.
She's married to the headphones, yes.
I'm married to the stream.
Yeah, she's married to the stream. Okay, let's z equal, yeah, imaginary part equals 0. So z equals real part of z plus imaginary part of z, which, well, this is 0, so it's just equal to the real part of z, and the conjugate of z is equal to the real part of z minus the imaginary part of z, which is also just equal to this. So ergo z equals conjugate of z. And then we can do it in the other direction. Let z in C, and we're assuming that z equals its conjugate, which implies that the imaginary part of z equals minus the imaginary part of z, which in turn implies that the imaginary part of z equals 0. And there we go. Okay. If z and w are complex numbers, prove the following equations. Oh god. This is just like... I understood that one. Nice. Do I want to do those? Ah, fuck it. Let's do this. Let's do this stuff properly. I just did like I already did all this stuff in the first semester, and I'm like, again. But yeah, let's do it. Let's do it. Gain more practice and never hurts. So what are we proving? That z plus w absolute value squared is equal to all this stuff. So absolute value squared means this is basically okay, let's fix some things first. Let's have x, y, x prime. Wait, no, that's gonna be annoying to write. Okay, let's just do AB. AB belonging to R4 such that z equals x plus I y and w equals a plus I b. Oh boy, complex analysis. Yeah. I'm just doing the, like, I'm just in the intro though, so right now it's just like basic properties of complex numbers and exercise to get you like used to them. So this is equals to the square root of like a bunch of stuff involving the real and imaginary parts of those numbers, which we can simply do x plus a squared. So this is the real part of z plus w right here. And then we got the imaginary part, which is going to be y plus b, all of that squared. And if we develop them, we are going to get x squared plus 2xa plus squared plus y squared plus 2yb plus b squared. I think this is gonna give us what we're looking for, which was what? 2z squared. The absolute value of z squared. That, okay, let's do some color coding here. Let's do green for the parts of z squared. We got this and this. I mean, the absolute value of z squared. Then we got red for w. We got this and this. And then we just gotta show that 2xa plus 2yb, or rather 2 times xa plus yb, is indeed 2 times the real part of z multiplied by the conjugate of w. Oh god. I really like messing around with complex numbers, but man, after once you've done the like trigonometric forms and the exponential forms, it's so annoying to go back to this like separating into real and imaginary parts stuff. Anyways, let's start simplifying. So we got our green parts, that's this. We got our red parts, that's this. We got 2 times xa plus yb. And now we just got to show that this is equals to the real part of, what was it, z times the conjugate of w. The simplest way to do that would be just to calculate the z times the conjugate of w and show that that's going to be equals to this. So z times conjugate of w equals what was it, x plus iy multiplied by a minus ib, because it's the conjugate. And we got our xa. That's good. What are we jamming to? I'm just playing the like mech music mega mix that someone linked in streams.gg. That was in the. So we got our xa, and we're only looking for the real part, so I'm just gonna ignore the stuff where we have an I left over. And we have iy multiplied by ib. That's indeed gonna be plus yb. And then we got I and a bunch of stuff we don't care about. So yes, this is the real part of z and the conjugate of w. So we're good. Next one is going to be just the same calculations. I'm not going to repeat them. Is there something interesting with this one? If z and w are complex numbers, prove that z plus the absolute value of z plus w squared plus the absolute value of z minus w squared equals 2 times this stuff. Okay. Oh! This is really easy. This is actually really easy. Once you've proven the the two above ones, just replace z plus w absolute value squared by this expression. Replace z minus w absolute value squared by this expression. The plus 2 real... The plus 2 minus 2 stuff cancels out, and you're indeed left with 2 times this. Okay, I'm not even going to write that out. Use induction to prove that for z equals some finite series of z1 to z to n, or some finite sum, w equals some finite product of W numbers, the absolute value of W equals what is this? Well, just the product of the Wait, you don't need induction. Wait, you don't need induction to prove this. If W is equal to some product of whatever, then like it's literally one of the properties right here. The absolute value of Z times W is equals to the absolute value of Z times the absolute value of W. Why are they asking to use induction? Maybe to like get you to practice induction proofs? And it's the same for this, like the conjugates are like the properties are right here. I don't understand why they're asking you to use a proof by induction. I'm not gonna do it. Let R of Z be a rational function of Z. Show that the conjugate of RZ equals R of the conjugate of Z if all the coefficients in RZ are real. Wait, what's a... Oh, Neyman, did you have trouble with taking notes when you started again, or with writing stuff on paper? No, not really. I did have one moment in the second semester where I was writing so much I hurt my wrist, and I had to stop taking notes for like a week or two, which honestly hurt my grades a little bit. Like I know like the topics that we studied during those that like week and a half where my wrist was hurting, I'm weaker on. But no, other than that, I'm usually pretty good at taking notes, honestly. Okay, show that. What is a rational function? I need to make sure I. Oh, it's a ratio of polynomial functions. Huh. Okay, so we have studied polynomial functions this year, but I'm not familiar with ratios of polynomial functions. In mathematics, a rational function is any function that can be defined by a rational fraction, which is an algebraic fraction such that both the numerator and the denominator are polynomials. The coefficients of the polynomials need not be rational numbers. They may be taken in any field K. Interesting. Let's see if I can... damn, my second note-taking. I just relied on brute force memory, but that's going. That's rough. I would not have succeeded my year the same way if I hadn't been taking notes properly. I have a friend actually. He's got really good memory and he's doing really well and all that stuff, but he doesn't know how to take notes. And I'm like, you should learn. You really like use the fact that right now it's easy to learn to take notes, because later on it's going to be really hard. I took no notes. I just sat in the front of the class and listened. I do that too. Actually, you know what? My best subject this year, which it was analysis, I did not take notes. But the professor gave us all his notes. So I was just reading his notes and actively listening and trying to... Like, not just listening, because I saw some people were, like, listening, but, like... and, like, reading along. I just mean-mugged the professor the entire time. Yeah. But like that works for sure. Did I ever consult ChatGPT for help? No, not a single time. Well, once on a project with a friend, he wanted to consult ChatGPT. So I was like, okay, sure, let's see what ChatGPT tells us. And ChatGPT was fucking garbage. It's terrible. It's terrible for mathematics. It's also really mediocre for other topics too. We had an English presentation, and he did his part in ChatGPT, and it's just like, it's really not great. Comp sci's goated. Yeah, I've heard. I'm a bit of a boomer. I know I should learn to use it if I'm doing programming memes, but I learned to program without ChatGPT, and it's just you young ones. Back in my day, we were flipping bits with cosmic rays. Okay, so RZ is a rational function of Z. Show that the conjugate, yeah, if all the coefficients in RZ are real. Okay, let's write this down and properly. So what we're trying to show is that let R Z. What would be the way of writing the set of rational functions? Let's not worry about semantics. I'll just, yeah, whatever. I'll just let RZ rational function. Le fuck? Hey Pandart, how are you doing? Comment ça va? A rational function in C. Oh yeah, Pandart. This is a little bit different from what you might have gotten used to when I was streaming regularly. I have gone back to school, to university, and I'm studying. I'm doing. Tu stream depuis combien de temps? Depuis aujourd'hui. C'est la première fois que je stream depuis. Voilà, depuis que j'ai arrêté. Yeah, this is now a homework stream. I homework. The year's over, but I'm studying still. So let RZ be a rational function in C. What that means is that there exists PQ in CX, the set of polynomial functions in C. Damn, feel lucky to catch you. You are lucky. You're a lucky boy. PQ such that R equals P over Q. CX, I know. I know, CX indeed. Right, and what we're trying to prove is that if all the coefficients in RZ are real... Mon pénis sur ton cul. Quoi? Ah, hey, salut, mon pénis sur ton cul. Okay, it rhymes. Nice one. Okay. What we're trying to prove is all coefficients of R are real implies RZ equals the conjugate of RZ equals R of the conjugate of Z. Désolé la fraction. Ah, P sur Q, mon pénis sur ton cul. Okay, yeah, that's true. So a Q in French means ass. So P over Q is the penis over ass. That's the joke here.
But P is also something else.
P is also something else. Oh yeah, P can be a fart too in French. P. That's the no.
Je pensais à P en anglais.
Ah oui. Oh oui. Yeah, P and P obviously in English is piss. So there you go. We got him. We got all the toilet humor out of the way. Okay. So, how do you prove a relation like this, an implication? We assume that all coefficients of R are real. So, that means that all coefficients of P and Q are real. That means that we have P of X equals the sum. I don't know. Let's assume n the degree of P. K equals 0. Let's call the coefficients. Let's call the coefficients small p. Pk times x to the power of k with p k belonging to all of the p's belonging to R n. You can maybe note it like this. And the same for Q. Though obviously Q could be of a different degree. We're going to call it M. Probably not going to have to use the degrees, I'm assuming. But does no harm to define them. Right, I'm not sure. I'm not sure about my notation here, by the way, but okay, so those are the things we assume true. We got all our P coefficients and all our Q coefficients real numbers. So when we evaluate, so let Z be a complex number. When we evaluate R of the conjugate of Z, we are essentially evaluating P of the conjugate of Z over Q of the conjugate of Z. We are obviously also assuming that such that R of the conjugate of Z is defined that such that Q of this is not equal to 0 because we can't divide by 0. Then we can just plug that into our sum expressions, I think, and use the properties of the conjugate, right? Yeah, we can just do that, right? So we got the sum k equals 0 to n p k conjugate of Z to the power of k over the same stuff for Q. And the thing is, we can use here the properties of the conjugate that we saw above, which are that the sum of the conjugate of two complex numbers is equals to the conjugate of the separate numbers, and the product of the conjugates is equals to the conjugate of a product is equal to the product of the conjugates. Oh, that was hard to say. So like the powers here will basically it's all just products and sums. So very quickly, if we develop that stuff, we are simply gonna get the sum. I'm not gonna write the indices again. We're gonna get this. And then we got ourselves a little fraction going on here. I think there's a property we can use for that, right? Oh no, I might be misremembering. I could. Okay, what can we do here? We can play around and do the thingy you do with the inverse of a complex number, because basically q of the conjugate of z is a complex number, right? Like right now where we're at, what we just showed is that is equal to the conjugate of pz over the conjugate of qz. I vaguely remember some kind of... Okay, so I vaguely remember from, like, complex numbers some kind of property where I think there was something where, like, conjugate of z over conjugate of w is equals to the conjugate of z over w, question mark, but I'm not sure. I might be misremembering, and it's not immediately obvious whether that is the case or not. Let's check, I guess. Let's check. I think it is the case, right? Because where we're at, that's the property we need. Conjugate of z over conjugate of w equals... we can multiply above and below by w, right? So we get conjugate of z multiplied by w over absolute value of w squared. And does that help us? I think so. Wait. Because if we look at the conjugate of z over w, what we get is yeah, this works. Z conjugate of w over this, and the conjugate of all this, and we pull the conjugate into the parenthesis, and we get the same expression. Okay, we're good. Meaning this is equal... Okay, so by this property we just proved here, a little, let's call it, I don't know. Let's star it. By the star property, we get, from this fraction, we get to the conjugate, this fraction is equal to the conjugate of pz over QZ. Why am I studying complex analysis? Because it's a book a professor this year recommended I study during my vacation. She told me it's very elegant and fun, and like it's beautiful mathematics, and I trust her, so I'm gonna work on it. There's some other things I want to study as well, but anyways, we got this, and this is none other than RZ, the conjugate of RZ. So we got it. The R of the conjugate of Z with our conditions equals the conjugate of RZ. Cool. Yeah, so basically I'm doing a double degree in mathematics and physics. Nice and pog. Thank you. Very pog. Obviously only if the coefficients in RZ are real. If the coefficients aren't real, then it doesn't work. Degree in Mad Max, yes. Hey, I gotta be ready for the apocalypse, okay? Mathematics and physics. From the definition of complex numbers, it is clear that each... Yo, thanks for the follow, Greener Dish. Each Z and C can be identified with the unique point that is the couple of its real and imaginary parts in the plane R squared. Yes. Right, Mathraxis, can you confirm? I can basically say that there is an isomorphism between R squared and C, right? The structure is conserved, and I can have a one-to-one mapping of all values in both fields, yeah? Sets, right? The addition of complex numbers is exactly the additional law of the vector space R squared, yep. If Z and W are in C, they then draw the straight lines from Z and W, yeah. These form two sides of a parallelogram with 0, Z, and W as three vertices. The fourth vertex turns out to be Z plus W. Note also that Z minus W, the absolute value of Z minus W, is exactly the distance between Z and W. With this in mind, the last equation of exercise 4 in the preceding section states the parallelogram law. The sum of the squares of the lengths of the sides of a parallelogram equals the sum of the squares of the lengths of its diagonals. Yeah, we get all the triangular inequalities and those memes. Yeah, I'm gonna go fast through some parts of this because this is literally stuff I just studied this year, so I don't feel the need to do the proofs again. If someone watching wants me to try to do them, then I'll do them, but otherwise I'll be skipping them. Yeah, the triangle inequality. One way to think of complex numbers is like you're working with vectors. Yeah, absolutely. That's how I like thinking about them as well. The main thing is you can multiply them, yeah. What I really like, though, with complex numbers is the like how much easier it is to do the trigonometry. Once you're playing around with the trigonometric form, using the Moiver and I forgot the other name of the, like the switching between the exponential and trigonometric form, you can prove all those like trigonometric relations so much easier. Moiver, isn't that a French name? Well, I learned mathematics in French, okay, so a lot of the terms are like I have to like Google them when. Oh yeah, Moiver's formula. Yeah, that cosine x plus I sinus x to the power of n equals cosine nx plus I sinus nx. Or I think you're just Americanizing his name. Yeah, Moivre. Formule de Moivre, if you prefer. The French version. On encountering an inequality, one should always ask for necessary and sufficient conditions that equality obtains. From looking at a triangle and considering the geometrical significance of 3.1, the triangular inequality, we are led to consider the condition of z equals tw for some t belonging to R, t greater than or equal to 0. It is clear that equality will occur when the 2 points are collinear with the origin. Yes, indeed. Alright, so this is just a roundabout way of saying that if we are in the complex plane, right, we got our A, I, B. So we got our triangular inequality, meaning like if we have a point Z and a point W. Oh god, you know what, I'm just not gonna draw it. Never mind. You all understood what was happening there. I'm not gonna be able to draw stuff like geometrically correct on this. I do have a whiteboard. Okay, if needed, I can bring out the whiteboard as well and put it behind me and like go full cam. But I don't think we need that for this. It's clear that equality will occur when the 2 points are collinear with the origin. Yes. In fact, if we look at the proof of 3.1, we see that a necessary and sufficient condition for z plus w equals z plus the absolute value of z plus w equals the absolute value of z plus the absolute value of w is such that the product of z conjugate of w absolute value equals the real part. I'd never thought of that this way. That's interesting. So yeah, that would mean that the product of z the conjugate of w is real. I didn't know. We actually, that's something we didn't see, that this is that z and w collinear. Z w collinear is equivalent to this. That is an interesting property. That's a new one for me. Multiplying this by w over w, we get w over w, we get the absolute value of w squared multiplied by z over w greater than or equal to 0 if w different from 0. Right. Wait, what? Oh, right, because if z multiplied by the conjugate of w is a real number, then z over w is also a real number. I was confused because of this, right? Like, how the fuck can you have an inequality between what's a priori complex number? There's no ordered relation between complex numbers, but it's not a complex number. Z over w, because we're assuming this this previous stuff is true, is actually a real number. So this is just the product of two real numbers together. By induction, we can expand the triangular inequality. And also useful is the triangular inequality with the minus sign in it. This one, I always forget it. Every single time I have to like I have a thing in my brain to like find it again really quick, but I can't remember it for the life of me. And it's basically the opposite of the addition one, anyways. Now that we have given a geometric interpretation of the absolute value, let us see what taking a complex conjugate does to a point in the plane. It's just a reflection, yeah, it's just a symmetry across the x-axis. Exercises. Prove 3.4 and give necessary and sufficient... should I do it? Nah, I'm not gonna do it. Fuck it, let's do it. I did it this year already, but it doesn't hurt to do things again, I guess. Alright, this music is not... Oh, it's Warhammer 40k music. Okay, it's like, this is not the kind of music I want to listen to for studying. Why does donating plasma have a higher reduction than blood alone? Oh, someone just linked something about reducing concentration of forever chemicals in your blood by blood donation. I would assume that works because they're probably more concentrated in plasma. Like if if solubility means it's more present in plasma than in the rest of your blood, stuff like that. Okay, are we proving triangular inequalities? I guess we are. When I proved it this semester, what I did, I think I used the decomposition stuff in, I think I used the decomposition stuff, like, just like here, if you're, to show this, first observe that, yeah, you got this relation. Okay, I want to kind of do this just because inequalities are kind of hard. So what are we trying to prove? We're trying to prove that for all ZW in C squared, we have the following thing. Less than or equal to Z minus W. Okay, so what this is basically saying geometrically is that the distance between Z and W is always going to be greater than the difference of the distances of Z and W to the origin. Right, because this is just the distance to the origin, and we're subtracting them, so it's the difference between the two. Is that yeah, that's the correct property. Okay. I wonder if there's like a more geometric approach to proving this, like using balls or something. Because you're basically establishing a relationship between the distances and stuff, but that would probably be a bit complicated. To prove this, what can we do? So some basic properties we need is we got the we got this stuff. Oh. And the same for the imaginary part, and obviously it's we got the same for the for a W. So if we go like full decomposition memes, we can probably skip some stuff. No, we did the proof with Z plus W, but we didn't do the Z minus W. Oh wait, we can reuse it. Yeah, it was the I remember what it was. You think the more we come, the more plastic we expel? The amount of blood being removed is higher in the 600 to 800 milliliter range for plasma because it's returned, while regular blood donations are around 400 to 500 milliliters. Oh, okay, interesting. Okay. Right. So we already know, because of stuff we did earlier, that Z minus W squared is equals to Z Z squared plus W squared minus 2 the real part of Z and the conjugate of W. Oops. Using this, we can let's see what they say here. I have a to show this first observer that we can have this. Oh yeah, then we can put bounds on the real part of Z conjugate of W, right? Like this is less than. Wait, it's negative. It's minus, so it's this whole part is greater than Wait, what am I? Wait. Let me just make sure I'm. So this means we have minus Z W less than or equal real part of ZW less than or equal to Z conjugate of W, absolute value. So if we multiply everything by -1, yeah, we indeed have this is greater than or equals to z squared plus double absolute value of w squared minus 2 times and this is whatchamacallit? Fuck, how do you call it again? This is the identity. It's the identity for a minus b squared, right? So the next, basically, all of this is equivalent to having z minus w absolute value squared greater than or equal to z minus the absolute values of z minus the absolute value of w squared. Then we can square root both sides, and that gives us z minus w squared greater than, and because we did a square root, we have to set this as positive, hence why we're adding the absolute value around the absolute values. And there we go. That's the proof. I did just copy the proof for the for the first version from the book, but hey, that's one way of learning. I ain't mad at myself for that. Oh yeah, give necessary and sufficient conditions for equality. You get equality if and only if okay. Equality if and only if the real part of z multiplied by conjugate of w equals absolute value of z multiplied by absolute value of w. Meaning, if and only if this is going to be collinearity again, right? It has to be. Real part of c by a conjugate of w is let's say let's have z equals x plus iy and w equals a plus ib. Maybe there's a way without doing the decompositions, but I'm just gonna brute force it. Z times conjugate of blah 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 is gonna be, okay, we got x a plus, oh yeah, it's the conjugate of w, so it's minus ib. Okay, yeah, it's plus yb. Plus yb equals square root of x squared plus y squared multiplied by square root of a squared plus b squared which is just gonna get us the square root of all that stuff inside, meaning we gotta get... I'm not sure this is the right way of going about this. Let's just do this stupidity till the end, I guess. XA squared plus XB squared. Yeah, no, this is not gonna work. This is not giving me anything. I don't think I'm wrong with starting off from this expression, but I don't think developing the... Let's make this... I don't think developing the... I don't think developing the real and imaginary parts is useful here. Yeah, let's just go back to the geometric meaning of all this, rather than do the algebraic, like, imaginary real part conditions. The geometric meaning of the 2 points being collinear with the origin is that there exists... Okay, collinearity. There exists T belonging to R starred, meaning without 0, such that Z equals TW. So now, okay, if we assume they are collinear, okay, assuming they are collinear, that means that the real part of Z law equals the real part of T multiplied by W multiplied by conjugate of W, which is just going to be a real number, because that is none other than T multiplied by absolute value of W squared, because the complex number multiplied by its conjugate. And on the right hand side we have Z W equals T absolute value of W multiplied by absolute value of W, and we get the same thing, T multiplied by oh wait, huh, I think T needs to be positive here. No, not never equal to 0. I think T needs to be positive here, because otherwise I can't take T outside of the out of the absolute value and like not consider when it's negative. So wait, does that mean I have to have them be collinear on the same... That's weird. No, like have them be collinear on the same side of the origin? It's like I imagine if we draw the complex plane here, if I have Z here and W here, it should work, right? Is there something that happens here that means I can ignore the sign of whether t is positive or negative? Yeah, I think okay, what if... Okay, let's just do this. Let's just verify this. If z equals minus w, then the real part of z multiplied by the conjugate of w is going to be equals to minus this. It has to. It has to be equal to the minus the absolute value of w squared. Yeah, no, we need the... Okay, so it's not just collinearity that we need. It's, I don't know how to express it. It's collinearity, but with positive coefficient, I guess, is how I would say it. That's so weird, though. And I never actually thought about what were the conditions for the equality. Okay, so this works. If we have t positive, and then going the other way around, we are assuming that... So we assume that the real part of z multiplied by conjugate of w equals the absolute value of z multiplied by absolute value of w, and want to show that they are... z and w are collinear, meaning that we want to show that there exists a t such that z equals a positive t such that z equals tw. That should not be that hard, actually. Let me think about it for a second. So I want to find a t that I can express as a function of like this stuff, right? That's what I'm looking for. Do I have to do it in both directions? Yeah, it's necessary and sufficient conditions. Necessary and sufficient means if and only if. Yeah. I need to think about this one a little bit. Okay, I think something I can start off with is squaring both sides. Because I want to find, I want to go from this to find an expression where I actually have z, zw, and some real number. That's like what I'm looking for. So if I square both sides, what's interesting is that in the squares of the absolute values of z and w, I will eventually be able to get... Oh yeah, of course t has to be positive, because... Yeah. Okay, never mind. Anyways. Right, so from those expressions, I can use the fact that, or I can try to use the fact that this is equals to z times the conjugate of z. This is equals to w times the conjugate of w. Then assuming they're okay, we're gonna do some divisions, so we gotta add some assumptions. And though those are trivial cases to cover, if z or w are equals to 0, we're not, like, obviously they're collinear and all that stuff. So we're going to start assuming that z different from 0 and w different from 0, which allows us to isolate z, and we know that z is going to be equal to this value. I just, for the sake of like simplifying notation, I'm going to also say that the real part of z conjugate omega squared, I'm just gonna call it, I don't know, tau. It's tau now. Just so I have less stuff to write. Why am I studying complex analysis? For the memes. Because it's, so this year I just did a year of, my first year of double degree, in mathematics and physics, and this is one of the books that one of my professors recommended I work on during the vacation, during summer vacation. So I decided to start doing it. I'm also gonna work on some physics stuff. I need to review some orbital, like, gravitation memes and some like basic mechanics that I feel a bit weak on. So I'll be probably streaming that as well. And this other professor of mine recommended another different book. This one's in French, so I don't know if it might be a bit hard to follow the stream along, but yeah, so I got like some physics stuff. Oh yeah, and I also wanted to start maybe get some advance on next year and study a little bit of electromagnetism. Is a double degree a regular thing in France? Regular? Not really. I mean, it's most people don't do that, but there are quite a few universities that offer it. Also, to be fair, like talking about it with different professors in my uni, well, one specifically basically said that like the double degree nowadays is not the same as double degree back in his day, where like basically the French government has cut a lot of hours from because of like budget cuts. I think it's very hard to do here because you can only enroll in one course at a time, so you'd have to get permission from the dean or go to private school. Well, yeah, the way it works here is that they designed the degree for it. Like the double degree, maths and physics, is not the same as doing both the maths degree and the physics degree. Basically, the maths and physics double degree is 100% of the physics classes and 80% of the courses and 80% of the mathematics courses. The idea is you can basically skip a few mathematics courses because it's stuff you're going to be studying anyways in physics, is the way it's been explained to me. And look, I'll be like, you know, studying books and stuff in my own free time, so my hope is to compensate for the 20% of courses lost if there's anything I'm missing out in there. Anyways, we got tau over conjugate of z multiplied by w conjugate of w, right? How do I turn this into like this expression? We aren't far away from it, but I think I should be isolating w. That's the meme here. Okay, let's rewrite this real quick. Like I see where this is going, and this is going in the right direction, but with the wrong letters in the wrong place. Because now that this doesn't. No, I'm dumb. This actually doesn't. Never mind. It doesn't change anything. So, okay, the problem I'm stuck on here is if I continue this this line of reasoning, I am going to end up with some real z equals to this factor of z. Wait, maybe we can do something with that, though. Maybe it might be a little bit of a roundabout way of proving this, but maybe we can do something with this. So I got tau over this. Because I'm multiplying top and bottom numerator and denominator by z, so I get back the absolute value of z squared, and I have this real number. Nah. This, yeah, no. I already know this is equals to 1. Okay, this isn't going anywhere. So I'm trying to prove that in this triangular inequality, the condition for the equality the triangular inequality is an actual equality if and only if this is true. And I think this is true if and only if they are. I know it's. Oh wait, no. I know it's an equality if and only if this is true. But I'm trying to prove that this is true if and only if they are collinear by some factor, some positive coefficient t. I can prove it in one direction, that if they are collinear by some positive factor t, then indeed I have the equality. So it's a sufficient condition, but now I have to prove that it's a necessary condition. And in the other direction, it's not that easy. So I'm starting off from this. This might be a red herring, the squaring both sides of the equation. This might not be the right direction to go in.
We are the music makers, and we are the dreamers of dreams.
So the problem is I need to turn this expression into something, some real number multiplied by w. Yeah, that's the thing. I'm still stuck on it, Mathraxis. So basically I'm like thinking about geometrically. I know it's about collinearity. I can prove it's about collinearity in one way, but now I'm trying, like, I can prove that collinearity is a sufficient condition to have the equality, but I'm trying to prove that it's also a necessary condition to have the equality, which is this part. So I'm assuming that I already have this, and that necessarily they become collinear. My thought is to do the same stuff as you started earlier in stream with Z. Yeah, I know, I know. I don't want to do it. I really don't want to do it, but I might have to. It's not. It isn't as exciting for sure. I really wanted to avoid it, but you're probably right. It's probably the best way of doing it. I was just hoping I could figure out a trick with like this, you know, taking it to the squaring both sides, and then isolating like z or w and figuring something out. Did you see conjugate of w is like reflecting? Yeah, of course, it's reflecting across the horizontal axis. Yeah. Yeah. Yeah, I think I might have to give up on this this specific path. Because, yeah, this is just another way of expressing one multiplied by z, so it's not really getting us anywhere. So I can multiply by w, top and bottom.
We are the music makers, and we are the dreamers of dreams.
If I multiply by w, top and bottom, then I have z equals tau over... Oh, wait. Maybe we can get somewhere with this. I have conjugate of z, factor of w, factor of the absolute value of w squared, and w here. Now maybe I can finagle something with this. Let's go back to what tau is hiding as well. Maybe it'll be clear. It's the real part of z conjugate of w squared. I don't think this will get us anywhere, but I wanted to look at it for a second. I have no... I don't see any simple way of proving that the conjugate of z multiplied by w is a real number. Right, like, okay, let's do the algebraic stuff. Z equals x plus y, w equals a plus ib. In that case, z times the conjugate of w is equal to xa, we saw it earlier, plus yb. That's the real part. Plus, and the imaginary part is going to be xb mine. Oh, whoa! I forgot it's the conjugate. Ya minus xb. There we go. What else have we got? We got this product here, right? We can play around with. We did that earlier too. Was some... I think so. I think we did that. No, I probably erased it. Anyways. Just trying to see if I could just copy paste the previous result. Anyways, yeah. What do we got? A square root of a bunch of shit. X squared plus y squared multiplied by a squared plus b squared. Oh yeah, I was looking. Yeah, I was doing this earlier, and this looks like it will get really annoying. I'm not sure this is the. I'm not sure this is the right approach. So then we get like all this. Xa squared plus xb squared plus ya squared plus yb squared, and all to the power 1.5. That does not look promising to me. So, like, right, we know this is equal to this. I'm not sure that helps us get anywhere near collinearity, though. This is interesting though. So we did all those proofs, like most of that stuff I'm doing right now already in this semester, but we didn't look at the at this specific thing, which is the proving the necessary and sufficient conditions for when the triangular inequality becomes an equality, strict equality. I don't think this is the right path. Like, looking at this, it could still be like separating them up into their real and imaginary parts, but not like this, right? Unless we combine both ideas and we square both sides of the equality. If we square both sides of the equality, we're basically grabbing this expression, right? And using what we have written just above, unless what we get then is x a plus yb squared equals to all this other stuff. Let's write it down like this for now until we need it. Until we actually need it, right? Then let's just develop the left-hand side here. Maybe we'll get something, because we get x a squared plus y x squared a squared plus y squared b squared plus 2 times x a y b equals to all this other stuff. And at least we have some, at least this way we have some stuff that's canceling out, right? Don't know if it really will help, but what we get is we get this, and this cancels out with this and this, right? We are left with 2x a y b equals to x squared b squared plus y squared a squared. I have no idea how this helps us though. So like at this point we're so far from what like Z and W that I have no idea where to continue with this. Unless I have an idea. It might not work out. Let's try to... Okay, so let's try to turn this into one of those, like, identities. 0 equals x squared b squared minus 2xa y b plus y squared a squared. This is that other identity, the a minus b all of it squared. This means that x times b minus y times a squared equals 0. Which means that x times b equals y times a. I'm teaching calculus next year first time. Nice. You just have to see these things, like splitting a term into 2 terms and then 2 steps later you cancel stuff out now. It takes so much practice for the intuition. Yeah. And I'm this is a good exercise for me, because those like really basic proofs, I really struggle with them. And harder proofs as well, but there is like this like zone where I feel really comfortable with, and this stuff gets me gets my noggin jogging. Okay, I feel like this result is useful, but this is not sufficient for what we're doing here. It does make sense, though. We aren't far away from it, right? Because what we're trying to prove here... I'm gonna go erase some stuff, because I'm getting to the limit of the page. Or I'll just add a new page. Okay. Add a new page, and... Yo. Where are we? Oh yeah, here we are. Add a new page and just copy-paste some stuff. Right. So we're trying to prove, we're trying to get z equals tw, which, looking at the algebraic forms, when we have x, what was it on the previous page that we just got? xb equals ya, yeah. When we have xb equals ya, that does work. That doesn't prove that z equals tw. We need more, but that is coherent, because this means we got x equals ta and y equals tb. So this is very coherent, right? Yeah, because then this is the same as saying xy equals xy, or tab equals tab. Now the problem with this is that how do I use it? How do I use this to prove this? I think that's a good result. Oh, stop. Okay. think that's a useful result, but I'm still missing something. Maybe I can use some of this stuff? Not really. Wait, is it possible? Is it possible to have this equality we just found and have Z and W not be collinear? I don't think that's even possible, right? Because this implies how can we? Oh, I've already I'm separating. Yeah, in the trivial case of the zeros is we're assuming they're non-zero because that's you're right, that has to be addressed, but it's like that's like the easy part. Oh yeah, what if, yeah, true. Okay, that one's true. What if Z equals 1 plus 0 and W equals 0 plus 1? Yeah. Then that does not work. And then we have this property and they're not collinear. Thank you. Yeah, that's the counterexample. No, that's good. That's good. I was starting to like wonder if it was sufficient, but it's not sufficient. It's coherent, but it's not. This isn't it. Though, okay, let's assume real quick. Maybe we can treat them separately. I don't like doing it this way, because then you get like 20 million separate cases where what if X is 0, what if B is 0, etc, etc. But let's assume none of them are 0. X, B, Y, A, non-zero. Then we get X over Y equals A over B. Programmer logic just asserts stuff. That does work in mathematics. It's just you still have to not forget to address the actual stuff you're like, if you're writing this in your proof, like, okay, let's assume this stuff. If you're trying to prove it for the general case, you still have to go back and be like, okay, now what if X is 0? How do we handle that? Well, that means that one of the other... Then, if X is 0, then either Y or A is also 0, right? Because we have this equality. So, okay, what if Y is the one who's 0? What if A is the one who's 0? So on and so forth. I took a comp sci math class that was all proofs before I took that linear algebra class, so I was exposed to math proofs then. Nice. I like proofs so much more than doing... technically this is a proof, but I like proofs. I like proofs where you're like actually reasoning around stuff so much more than like playing around with like mathematical expressions. But hey, you gotta be able to do it too. I don't know, the other path that I didn't... Hey, Dup. Thank you. Hope you're having a good day too. The other path, just to go back to the beginning of all of this, the other path I was thinking of to go about this proof is to just find a value of t where all this works out and have it like descend from the heavens, where like assuming this true, I just get a t. I just define a t such that it all works out magically. And that's kind of what I was hoping to find with playing around with the numbers. Rather, I wasn't expecting to like look so much as look for direct proof, as much as find hints as to what the t could look like to prove the collinearity. But well, if we assume this is true, then I have wait, if we assume this is true, I get like this stuff down here, right? But let me think for a second. I assume this is true. Absolute value of z equals to real value of c conjugated w over absolute value of w. But I also want absolute value of z to be equals to t times absolute value of w. So I'm looking for t equals, or rather, I need t such that it's equal to this. Okay, this might be way simpler than what I was about to do. I should have just done this from the start. Okay, this is going to be way easier. Because now that the value of t has descended from the heavens upon us, okay, I need to erase a bunch of stuff here so I can continue. So it stops. Blessed T Praga. I love those proofs. Like the, you know, when I'm like reading my professor's PDF, and it's like, we are going to prove the limit of like this and this and this and that, and it's like, well, delta is equal to the minimum between this and that, and it's like, delta has descended from the heavens of his intellect and has blessed us with its presence, and it all just works out magically. And like, obviously in class he tells us, well, that's the hard part. It's figuring out what the value of delta has to be to verify the inequalities and everything. You want to see the worst of magic variable? Yeah, I'm sure you got some good ones. Okay, but yeah, this should be easy. So let t equals this. Obviously, we need as an extra condition w different 0. Otherwise, we can't divide by the absolute value of w, right? So, okay, yeah. Let's start off from. Let's do this. Delete this, make some space. Okay. So we're assuming this true. Now I just need to show that the real part of z conjugate of w over absolute value of w squared multiplied by w is going to be equal to z. Using this property above, right? Though we have a problem. I believe we might run into a problem. Because I found the value of t only using the absolute values, and now I need to like have an actual. Let's see where it leads us. My Algebra 1 students are dumb as fuck. I keep putting on every exam a problem that involves x plus y in parentheses minus open parentheses 2x plus 2y close parentheses. And they consistently fuck up and freeze whenever they see the minus before a parenthesis without a coefficient. My deal with students is it's 3 points, and on every exam until someone in the class gets 100% on it, it will go away. That seems fair enough. It's the same 2-3 students who fail at every test. COVID fucked their learning up hard. Yeah. Not to go too far in the boomer memes, but it's definitely something I felt in class too. Like my memory of when I was in high school, in my class, the mathematics level was like quite a bit better than what I've seen in uni this year. Of the students, I mean. Doing some complex analysis? Oh shit, yep. We sure are. Wait, why don't I see your message show up, Andy? That's weird. I see it show up on the stream, but not on my chat box. Wait, can I refresh it? Might have to refresh it. Fresh chat. And the shadow band aware. Maybe. It could be some like, but I'm not multi-streaming, so I think if I recall correctly, I was too lazy to set up multi-streaming for it today. Yeah, Andy, your shadow band. Sorry to be the bearer of bad news. Bad news bear. Okay. How do I prove that this is equal to z? Well, this... Yo, thanks for the follow, Alphonse101. This is none other than... Oh yeah, since we're assuming this true, then this is none other than absolute value of z over absolute value of w multiplied by w. Yo, thanks, Viscosity. Medical doctor, I don't understand what's happening, so I followed. Just doing some mathematics. That's pretty far away from medical studies for sure. Absolute values of z. I'm trying to. It's some basic stuff, but I'm trying to prove that in the triangular inequality, which is this one, the triangular inequality with the subtraction in the complex numbers. In the complex plane, the inequality is a strict equality if and only if z and w are collinear by a positive coefficient t. So I was able to prove that if they are collinear, then indeed that is a sufficient condition to have the strict equality, but I'm struggling to prove it that it's also a necessary condition. I like your funny words, Math Man. Thank you. Appreciate it. Okay, another way we can look at this is that the absolute value of w squared over the real part of z multiplied by conjugate of w multiplied by z, this should be equal to w. For now, all we know is that it is equal to absolute value of w over absolute value of z multiplied by z. How can we use those two things together? One way of proving equality could be if we manage to prove that this over this multiplied by w is minus z equals 0. That would work if we prove this. That would be one way of going about it. Oh, okay, I'm gonna be cheating. I'm gonna be cheating, but oh wait, is it cheating though? Okay, I think this is equal to 0 because if they're collinear. This is the bizarre defined magic thing. Absolutely no intuition. It is just works thing. I've thought this class 3 times and never have seen an explanation. Polynomial interpolation error formula. Oh god. Okay, this is way beyond my level, by the way. Just FYI. Theorem 5.9. Let f belong to the class of n plus 1 differentiable functions over the interval ab, and let the distinct nodes x0 to x until xn be in the interval ab. Then for each I don't know what the meaning of the bar over the x here is. Are we in complex numbers? Is this a conjugate? With conjugate of x different from xy, there is I forgot this Greek letter belonging to AB such that no, it's all real numbers. Okay, continuous when differentiated at least n plus 1 times. Yeah. Oh yeah, it's not just differentiable, it's continuous as well, yeah. Class n plus 1 is the term I learned. So... Wait, this is... Isn't this... Ah, I know this stuff, I think. Series expansion. Isn't this the Taylor? Doesn't this have to do with the Taylor expansion of a function? E underscore n of x is the error in estimating the function f of x with a polynomial px based on sampling the function at different points on that interval. Different locations x will have different errors. Anyway, the point is the thing I highlighted just comes from the heavens to complete the proof and has no intuition. Yeah. I got you. Yeah, the relationships rely on Taylor expansion or Taylor remainder theorem. Yeah. Cool. Yeah. I like it when I read stuff and I'm like, I can understand this. That's a good feeling. I know what this builds upon. I recognize stuff. That's a good feeling. Right, so we got a Taylor expansion. Let p n plus 1 be the polynomial of degree over n plus 1, lesser than n plus 1, which interpolates fx at n plus 2 nodes. It follows that the Taylor remainder, Taylor's formula, if fx has derivatives of all orders in an n open interval I containing a, then for each positive, yeah, this is the Taylor expansion. And yeah, this is the remainder function. I agree. Though we haven't really gotten into detail in class. We've seen Taylor's formula, but or the Taylor expansion, but we haven't gone into detail on what the error function is. The only thing the only thing we've done with the error function is we stopped at hey, what's down here? Oh yeah. You get to just stop the Taylor series exactly. Yeah, I know. Yeah, and instead of truncating the infinite series and saying it's an estimate, it's more useful for proof. Yeah, because then you actually have a real equality between your function and the expansion, because you have like all the errors shoved into that. Yeah, and it's really useful for proofs. Absolutely, I've used it for that. Right. So what we have been doing. We get like fx equals, let's do it in like 0. F prime, wait, no. F0 plus F prime 0 x plus etc. The Taylor expansion. And then the way we've been writing down the error is x to the power n, if we do it to the nth order, x to the power n, and an error function we call epsilon of x. And then the condition we have on epsilon is just that limit of epsilon in 0 equals 0. That's how far we've taken it in our class. Though it's also weird because like the first semester was a very like the first semester where we saw the Taylor expansion was like continuation of high school calculus, so it was very selectively rigorous. It was more rigorous than high school maths, but it was still very like wishy-washy on like it's a bunch of stuff was assumed true that we saw in high school that has never been rigorously proven, right? Like we didn't go into what actually derivation, what actually is a limit, what actually is derivation. And then in the second semester, the professor is basically like, forget everything you've learned. We're starting from properties of the real numbers, properties of complex numbers, and that's it basically. And we're just doing we like define supremum, infimum, the like basic topology constructions like neighborhoods, and from that we constructed limits, and like basically took us an entire semester to, but it's cool because we proved that stuff like really rigorously, but it took an entire semester just to get back to where we were at last semester. And so we didn't actually see the Taylor expansions in like a more rigorous context. Though we did see the equivalence between f is derivable is equivalent to there exists f of x equals to f, the derivable I should have written in A, plus f prime A of x plus our like error function, whatever you want to call it. I should not have. That was my attempt at some weird Greek letter. Let's just call it O, OX. And like this is strictly equivalent to I shouldn't have called it O. Now I don't know what's a 0, what's an O. And like that's like that was useful. I actually used that on the exam. There was a limit where part of the proving the limit required proving that the limit of sinus x over x. So I used since we were allowed to assume the properties of the sinus function, I used this this expression for the sinus function, and then the limit is really easy to prove. Anyways, I'm getting super sidetracked here. I should just, why am I trying to like, I should just do this. There we go. But yeah, and then talking with professor the other day, I realized the derivability, a function being n times derivable, is strictly equivalent to the nth, to there existing the nth Taylor expansion. Like if you prove that there exists the nth Taylor expansion, nth degree Taylor expansion for a function, then you also proven it's derivable. Though usually you do it the other way around, right? You first prove it's derivable n times, and then you just can build the Taylor expansion. But I think it's funny that it goes in both directions. It's like neat. I don't know if it's really useful, except for like if derivable once, then it can be useful, I guess. But otherwise, I don't really know. Where was I at? So I want to show that this. I've never seen it proven with the center being series expansions, but I can believe it works. Yeah, I think I don't know if I have the PDF here. Let me pull it up on my other screen so I don't like dox my school and stuff. Oh wait, no, I don't need to do it this way. Oh, it's going to be in French, so I don't know if it's going to be that useful. Let me see. Limits of functions. Oh yeah, derivatives. Oh yeah, this is how you call it. Oh yeah, it was with a mu symbol here. So proposition 6.1, the following properties are all equivalent. that this limit. So like those two definitions are the classic ways you look at durability in one point, right? You take like your compared. I don't know what like the English term would be for this, but you know when you compare the change, and that is strictly equivalent to this, which is basically just the first order Taylor. You're already on your first order Taylor expansion, right? And then there's the proof down here. So you can just, you know, prove the implications in all the directions. Yeah. That being said, let me put some music on. Oh, it's getting late, actually. Okay, let me think, like, let me give this like 10 more minutes, and then I'll stop and we'll eat dinner and stuff. I'll pick this up tomorrow, probably, or yeah, I think I'm free tomorrow. So, I was memeing about the T. Define my T. Such that it has to be equal to this, so that both those things are true. And if both those things are true, then T has to be equal to the real part of Z multiplied by the conjugate of W over the absolute value of W squared. I mean, we can, okay, because what we're assuming, our hypothesis, it's only about absolute values. So maybe we just gotta keep on turning stuff into absolute value, like use absolute values, right? So oh my god, he's live, sheesh. Yo, Kyoshiro, this is not gonna be your favorite kind of content though. I'm doing nerd shit. How are you doing? So one way I was thinking of looking at this, it's a bit cheating since at that point in the book I'm studying, they haven't introduced the exponential form of complex numbers. But like this is equal to absolute value of z multiplied by I argument of w, right? Which, if the argument of w equals the argument of z, which is, you know, basically collinearity, then we get that this is equal to z. But that's what we're trying to prove. We can't just assume it's true. Doing great. I just got my final exam results back and I succeed. Yo, good job. Are your studies over? Are you done with your diploma? Congratulations. Yes, I'm done. Good job. Time to come out into the real world and work and regret not spending more time studying, because those times were chill. Nah, I'm sure you'll do great. It is a relief as well to, you know, move on to greener pastures, to new things, to do what you actually want to do in life. Yeah, real world Sag. Yep. Okay, this is really bothering me because basically I can't assume. I'm missing something. I'm missing something in this proof. Like, how does this... How does this get me collinearity? How does this get me... Because all I'm dealing with here is... I think I'm too focused on the right-hand side of the equality. The right-hand side of the equality is only giving me those absolute value memes, and I've played around with them. We got halfway there, but it's not enough. What we need is the like this argument thing. We need the actual angle of our complex number, some condition on it. So I think I actually do have to look at what this real part means. Okay, I'm gonna just keep cheating and use the exponential forms, because I need to. It's not even maybe I'm not even gonna use them for the proof, but just to understand geometrically what's happening here, right? So this means the real part of z times the conjugate of w. Z times conjugate of w. Let's have argument of z, we'll call it theta. Can I use real z equals 1/2 of z plus conjugate z? Oh shit. Oh shit, I'm dumb. Oh no, I think that's... Yeah. Wait. That works, probably. That sounds like it should work. Oh no. Right. So this means, using what you just said, this means we have 1/2 of z conjugate of w plus conjugate of this, meaning conjugate of z times W ZW, right? Then I think we can play around with isolating, just straight up isolate some Z and W, like keep Z on the left hand side and W on the right hand side. So then we got Z W equals. Oh, but the minus is not going to be very convenient here, is it? Okay, I think that, this is going to work out, actually. Yeah, no, this is going to work out fine, I think. Let's do this so we're clear on what we're doing. So we've isolated Z. Let's write out all this calculation steps. This is something I learned this year. I used to be the kind of guy who would constantly like do stuff in his head and skip the calculation steps on my in my work, and that's not what I've been doing this year. Obviously we got W different 0. I already wrote that above, but it doesn't hurt to write it again. Then we have multiply above and below by W, right? So we have 2 absolute value of Z over absolute value of W, because W conjugate times W is absolute value squared, minus Oh, I'm gonna have a little bit of a problem here, though. I'm still gonna have a little bit of a problem here because of the conjugate of Z that I'm carrying over here. I might be able to get rid of it somehow, perhaps. Oh yeah. Wait. Let's just keep doing this. Let me think. This is like so close to what I want to get. Anyways, we do get conjugate of Z multiplied by W squared, which is like this. Okay, this part of the equality is annoying. I'm not sure where to go ahead with it. This is so close, right? Okay. Let's continue the great adventure. So I can factor by W. Right, I got Z equals to... And like, okay, this part obviously belongs to R plus. This satisfies our need for Z equals TW. But this conjugate of Z over conjugate of W, that's just not it. That ain't it. Perhaps we can work something out. It's gonna leave us with like W squared and jazz. So I'm thinking we can multiply, divide by Z, multiply, divide by W in this fraction. At least get rid of the conjugates, but we're going to be left with an expression with a real number multiplied by W over Z, and that's not do it for us. Maybe using some other property we looked at earlier. What did we have? Yo, Joseph, thanks so much for the Prime sub. We did have XA plus YB. We were messing around with some stuff earlier. Oh wait, no, those are different proofs. Never mind. Oh yeah, there was the stuff I deleted. Okay, I deleted the proof, but we did have an interesting property here, which was that if we do the decomposition over real and imaginary parts, and assume that everything's non-zero, x over y equals a over b. We do have some proportional, the ratios of the real and imaginary parts are necessarily equal when we assume this. Does that help us here? Not really, but maybe we could do something where that does help us. Well, for that we would have to figure out a way of arranging stuff that we have like the real part of W over the imaginary part of W, and the same for Z. That might be way too complicated, but it's something to keep in mind. Yeah, I think this is gonna be a good place to stop. I'll eat something, I'll sleep on it, and see if I get any better ideas tomorrow. And worst case, I'll just continue the book because this is not. Or I'll like look up. I'll think about it. I'll see maybe I'll look up online if there's like a solution for this or whatever, or see like what some other PDFs say. Because this is not really an important part of the book. This is just supposed to be practice for familiarity with complex numbers. Alright, I don't know if I'll stream. I'm not gonna stick to like a hardcore, like a hard schedule or anything with me streaming again. I'm just doing this for fun and because it's fun to, you know, like have company while I'm working on stuff. So if I work tomorrow, I'll stream. If not, then it'll be after tomorrow or something like that. Thank you for watching. Thank you for hanging out, and bye bye. See you.